Hi, this is an example problem about Rayleigh's criterion for resolvability. This is from chapter 7. Pause for a moment to read the question. So here we have a case where we've got a telescope and we're going to try to resolve two features on the moon. So here's a bad picture of the moon here, part of the moon, and we've got, something on the surface like a crater, right? So if we want to try to resolve the crater, we need to be able to see the distance that spans across from edge to edge. And we are looking with our telescope, which is, really far away over here somewhere, right? And if we think about it, the two edges of the moon, they are going to, go to the telescope with some light, and they're going to produce an image there. And on the back side, as it passes through, this image is going to continue to spread out a little bit. But because they pass through the diameter here of this lens, you're going to have some diffraction going on here, which can cause these two images to blend together. And if they blend together too much, we can't resolve them. Rayleigh came up with a criterion for when is the limiting amount. What's the smallest angle we can have here, in other words, so that we can resolve that there's two distinct images. We can see distinctly the two edges of the crater, therefore we can resolve the crater. Here's some notes on Rayleigh's criterion. So if we look at like two images as they would appear, here's the center of the images, the central maxima. And in this case, you can definitely tell there's two images. Over here, look at that the central maxima of one overlaps with the first minimum of the diffraction pattern of the other. And this is the case that Rayleigh said, these are barely resolvable. We can just tell that there's actually two things there. It's an arbitrary criteria, but Rayleigh made it up and we use it. Now, what that means is all we need to do is figure out what is the angle to the first diffraction minimum. And so if we go down here and look at an equation, this is similar to a single slit diffraction pattern, but in this case we have a circle of diameter d, and you get a circular type of diffraction pattern. The equation we have is almost the same as for single slit diffraction. This would be for the first minimum, which we care about, but we get an additional factor of 1.22 because of the circular shape. Now, whenever we're looking at this angle here, theta dark 1, it's always a very small angle, and so if we're using radians, or a degree less than 15, but we have to use radians, we can say that this sine theta here is approximately equal to theta if we use radians. And so we can simplify this a little bit further. And so this here is Rayleigh's criterion. This is his equation that tells us what is the minimum angle for resolvability. So let's go ahead and use that equation. So theta for Rayleigh, remember it's got to be in radians, equals 1.22 lambda divided by the diameter of the aperture or the lens. In this case, I should make this a lowercase d. That's the diameter of the Hubble telescope. Now in this case, this is easy to figure out what this Rayleigh's angle is. So we know it's 1.22 times the wavelength. We're using 600 nanometer light. Let's get this into meters so we have consistent units for the lengths. The diameter of the Hubble is given as 2.4 meters. Here it is. That allows our meters to cancel, and we're going to get an angle here, and it's going to be in radians. It's equal to a very small value, 3.05 times 10 to the minus 7 radian. So this angle for the Hubble telescope used with that wavelength, that is the minimum angle which we are able to resolve. Anything smaller than that, we will not be able to tell that there's two distinct images. Now so that was part A. Now for part B, they're asking us, what is the smallest crater we could resolve on the moon? So we already kind of drew the picture. Now we're going to assume that the angle there is Rayleigh's angle, and so we're going to see what's the smallest, crater here. What's the length there across that we're able to resolve? Well, the distance from the moon to the Earth, we can draw a straight line here, from here all the way to there. That is a length of 2.4 times 10 to the 8th meters. Now, how are we going to relate that to the distance here? Well, I'm going to call this length here S. Now, there's a couple ways to think about this, but there's a hint that says use the arc length formula, S equals R theta. So again, this is a, we can imagine that if this is the center of a circle, and this is the edge of the circle here, this is like an arc length, S. That arc is a little bit curved, but look at how small this angle is. It's so tiny that that section is going to appear straight for S, essentially. So we can basically use this arc length formula where if I multiply the radius, this is like our radius, times the angle in radians, then I'm going to get the arc length S. So if I do that, S is equal to R theta, and R in this case is equal to 2.4 times 10 to the 8th meters multiplied by 3.05 times 10 to the minus 7th radians. And remember that as soon as we multiply something with radians by meters, we can just drop the radians. It's a dimensionless unit. Multiplying this out, we get a value of 73 meters. So that's the minimum separation that we can still resolve. If it's less than 73 meters, then it's going to be smaller than the Rayleigh angle, and the Hubble telescope will not be able to tell that there is actually a crater there. Oop, I see that I forgot to put in the additional bit right here. That's 2.4 times 10 to the 8th meters. Luckily, I put that in my calculator, so the answer is still correct.